Good afternoon, everyone. Thanks for coming to this talk on Hdfs evolution. Sorry. In response to big data trends. My name is Sanjay Radia. I'm an architect and founder of Hortonworks. I was part of the Hadoop team at Yahoo since 2007. I was the chief architect of the core of Hadoop that was, Hdfs, Yarn, MapReduce at Yahoo. I've been a long time Apache committer and PMC member, and I've designed and influenced a number of products in Hadoop. Prior to that, I was at a startup and at Sun Microsystems, and prior to that, I was at University of Waterloo where I did my doctorate. So give you my talk is going to start with a very, very quick 1-2 slider overview of Hadoop. So make sure we are all on the same page. And then I'm going to kind of spend a little bit of time on trends in hardware, trends in application, and deployment models. And then start talking about how does Hdfs and Hadoop in general start addressing some of the trends, architectural changes in storage, archival, microservers, public clouds, private clouds, VMs. In a couple of these areas like microservers, for example, I talk about what the issues are. I might not be able to give you a complete answer on what's the right thing to do there. But in other areas, I kind of tell you about either things that we've already done or things that we are planning to do. Okay. So basically, Hadoop is a platform that is scalable, reliable, manageable. It scales I/O, storage, CPU. So you typically have racks of machines. Okay. And usually it can take anywhere from 3 to about 6,000 nodes. Clusters, in fact, slide is slightly out of date. At that time, a few years ago, the largest cluster we knew in existence was in production was 120 petabytes. Right now, the largest cluster in production at Facebook is 200 petabytes. They now use the federation, the backported federation from open source, so from the main branch in Hadoop to their branch. Okay, and the main kind of thing about Hadoop is Hdfs is completely fault tolerant to node failures, disk failures. It doesn't use RAID controllers. It basically deals with JBODs and deals with the failures of those nodes. Okay, and because of this kind of automated management, we know customers who are using about one operator per 3,000, 4,000 nodes. So for example, Yahoo has one operator per 3,000 to 4,000 nodes. And partly because that basically means that as nodes and things die, you really don't have to do anything. Okay, you basically worry about are you losing capacity, and then you replace nodes when you think it's important to replace the capacity. Okay, and the storage server, of course, is used for computation, and data is moved to the computation. Okay, Hdfs provides a file system. It's not a SAN. Okay, it supports read, write, and append. It supports random reads, but does not support random writes. Okay, and more recently, we have moved away from a kind of a MapReduce execution engine to a completely general execution engine that lets you run not only other Hadoop ecosystem applications like graph processing and streaming and SQL, okay? So things that are normally now considered part of Hadoop ecosystem, but really it makes the infrastructure available even to non-Hadoop applications. So we have something called Slider. I think there's a talk on that here. And that really means you can even run other kind of services, okay? I'm going to skip the architecture slide. I think most of you are kind of familiar that, you have a couple of masters, a master for the name node, a master for the yarn part, both of them highly available, and then you have a bunch of slaves that are used. I'm going to kind of not go into a lot of details here in how the heartbeats and things work because it's not really relevant to the talk too much. So the kind of trends we see is the biggest one, of course, that I mentioned here on the left-hand side. Let me see if I'm okay. Really, is the big platform changes, network bandwidth changes, the number of cores on a processor, memory sizes, flash storage, disk density, disk storage size, spindle sizes. the use of virtual machines. Virtual machines have been there from early days, but now we've been seeing them in some production clusters, customer, and I'll spend some time on that, microservers. The other one, of course, is the private and public clouds. I'll talk a little bit about there, what works well, what doesn't, what are the changes we need to make. Application streaming, machine learning, and really Hadoop over the last couple of years has started to also address interactive workloads in addition to the traditional batch workloads. The data sizes, in some sense, people are focusing also on smaller data sizes that fit in memory. Okay, so normally you see systems start from small and then start handling the larger sizes, and Hadoop has kind of been the opposite. It always worked great for large sizes. We never bothered to optimize for the small, and now we're kind of moving towards optimizing for the small. Okay, of course, it used to work for the small, but we never optimized for the small case. Okay. So you see, clearly more cores, faster memory, I/O interfaces improve in performance. Okay, storage density 4 terabytes and up now. The disks are traditional spindle disks. I/O, but typically the I/O throughput and latencies are the same for the spindles. They don't improve dramatically over generations, but flash storage is something that has become more and more economical over the last few years. And the other one that is also is we see customers now saying, you know what, I want to use RAM and put RAM not just for my application processing so that I can run more applications, but actually use RAM to my advantage to make the applications run significantly faster. So we see customers saying, you know what, if I was going to put 100 gigs on a node, I'm willing to put an extra 100 gig just for this special purpose. Okay, so that has changed. More number of cores, as I mentioned, and cluster networks. People have mostly moved. A lot of people have moved to 10G network. Okay, and we have some cases of InfiniBand, especially when you see appliance-style boxes. So there's some manufacturers that have created an appliance Hadoop cluster. So you kind of get this cage with a whole bunch of processors, and often they will use InfiniBand internally. Okay. The interactive applications, as you see, Stinger, Tez, Impala, they all move towards using a lot more memory. They're much more latency sensitive. Okay, and even in batch, we see streaming becoming extremely important, graph processing, machine learning. Okay, so lots of changes occurring. The other one that is really cloud Hadoop as a service that's starting to take off, where people are not just thinking, oh, I'm going to run this on Amazon as an experiment, or because my data is already on Amazon. So people are now seriously looking at, do they create an internal cloud that basically changes the cluster sizes dynamically, maybe share it with their own other private VM cloud for other applications, and then some customers also looking at maybe seriously moving to a public cloud. Okay, and what are the issues over there? So the first thing I'm going to talk about is something called heterogeneous storage. There's actually a talk yesterday that was presented by my colleague Chris on heterogeneous storage. I'll talk about that, and I kind of take how that architectural changes, not just some of the immediate things, but what it'll let us do down the road for this. So basically what happened was the original Hadoop architecture, each node had a bunch of disks, and the system just said, this is my storage, it's one pool. If you were to add flash to this, yes, it would run faster, but if some nodes had flash and some nodes did not have flash, the system would not know how to take advantage of that. It would not tell applications how to take advantage of that. Okay, so in the new architecture, basically what we've done is that the system does know that there are different kinds of media. The media could be, spindles. The media could be an SSD. The media could be memory. And we are also looking at treating things like S3 Swift also potentially as a media, and I'll kind of give you examples of where that can start fitting in. Okay, so that's more future looking, but the heterogeneous storage architecture change where the data nodes now know the media type. They also send that information to the name node, who also sends it to the client. So basically what that architecture change means is that the name node now can make allocation decisions about where to put things. And you can also tell clients where to go. Okay? So basically what we are trying to do over there initially, of course, is well, I can cover that in this slide a little bit later. So basically what the kind of things we want to move towards is really automatic tiering, so that we can move your data from different storage types, from SSD to flash to memory, okay? And the other thing is that we may also want, where in the early days, it's kind of hard to get that level of technology and doing tier movement. So in the early days, what we're really going to focus more is, you could say that I want stuff in memory, okay, or you could say that I want one replica on an SSD, for example, or all my replicas on an SSD. So initial work is going to really be enabling this device to be accessed, okay? The first piece of work that is already out there in the upcoming release in Apache and also in my company's own product is basically memory to be used for caching hot files, okay? And that basically means right now the interface is kind of manual, where the operator says these are the files I want to pin, and the operator arranges to make sure that the files that he pinned in memory actually fit in memory. So this is great for if you're a customer and your specific data sets. You could say my daily data every day is being tagged to fit in memory, so my system runs faster. Clearly that is not something that can be managed long term, and so we want to fix that to make it much more automated. The second thing that so that you figure out what are your hot files. The second thing that we are also working on is to use memory for intermediate files, okay? And so the work that we've done in the architectural change at this level does it. So in fact, it treats memory almost like a device, and it reports it that, by the way, this data does sit in memory, and the DFS client can send the clients over there, okay? As we start, the other thing is that we also use quotas for storage types, which means that in a multi-tenant environment, if you've got limited SSDs and things like that, you can manage the scarce resource of memory and SSDs, okay? And that fits into our overall original architecture, where we used to have quotas. So now quotas can also be by storage types, okay? The other thing that we are starting to do now is to offer APIs in Hadoop to move data between the tiers. And so the first thing we're going to tackle over there is this intermediate file. So we're going to kind of plug in APIs into our query planner. So we'll say, I want this data in intermediate. And as we start doing that more and more, it kind of turns Hdfs from a filer or a file system or a storage unit to more like a data fabric, because it's very closely tied and has hooks into the upper layers. So it knows and is dealing with data and how data should be placed, rather than I'm just storing data and you decide where you want to place it, etc. And so that's why we were saying it moves towards a fabric. And you'll see this, some of what we're coming out with this intermediate files and the hooks for that into the applications. And down the road, as we get the tiering stuff done, adding hooks for this. And so this is going to be probably one of the big changes, and the architectural change that we did for heterogeneous storage kind of laid the underpinnings, okay, to do this work. Okay. The other one that we are seeing a lot of customers is saying, okay, what shall I do about my archival data? Hadoop is a model where you, are talking not about data that you store for 6 months or a year, because it is, in the order of 10 cents a gigabyte. You're now talking about storing your data for 3, 4, 5 years. Okay. And most customers don't want to put this on tape because they want, unless it is just for legal reasons. If you're required to store your data for legal reasons for 5, 6 years, you may seriously consider putting on tape. But when you look at the big data space, where you want to get intelligence out of your data, you often want to say, let me look at how things were 5 years ago, why the properties that I'm seeing my customers have today are what they're true 5 years ago. And so you occasionally want to go to data that 2, 3 years ago. And so therefore, archival that is online is important. So usually there are two models that are actually being considered. One model is that you have a separate cluster. In the separate cluster, you tend to buy, let's say, a low-powered node, and you put regular spindles over there. And that one, basically, you say that, you're kind of saving on the cost of the hardware. But this one is a serious drawback, which is that spindles are the big bottleneck in a big data system. And you are actually really much better off taking those spindles and putting them Because if it's the same kind of cost of the disk, you're better off taking those disks and putting them in your main cluster, and in a sense spreading your cold and hot data across, which means your hot data now has even more spindles, and therefore your system will be even faster. Okay? In fact, you want to go to the extent that you place your hot data on the portion of the disk that are the fastest. Okay? And you want to kind of move to that model rather than take your cold data and move it completely out, because spindles are the bottleneck. So really, rather than have an archival cluster, you're better off doing something like that. Now, the place where an archival cluster more makes sense is if you have a storage device that is actually, say, slower and less and much cheaper. In that case, you really may want to create an archival cluster. And there, basically, you could create an archival cluster, or in fact, what we are really looking at more is to say that put those archival disks on your main cluster and let Hdfs move your cold data into the archival storage. And as the thing I talked about a little bit earlier, you can see how it fits into that model. And in fact, you can even start playing games like, as my data gets, say, from hot to warm, I could say, you know what, I'll keep 2 replicas on spindles or SSDs and move 1 to the slower archival disk. So I get my 3 replicas for backup for reliability reasons, okay? And so that's what we see if, lower cost, slower spindles as a technology takes off. So for example, we know somebody at Facebook who is trying these lower cost spindles. We'll see how they work out, and that's how we see them fitting into this architecture, okay? The other one, of course, is nothing to do with technology. Hardware technology is that erasure codes. Again, this is now right now moving. There's work being done at Facebook on this that we plan to take and incorporate, which is basically your cold data goes into erasure codes, which means you don't have 3 replicas, but you really have 1.6 replicas, okay, the 6 being the erasure codes. So that's with that. The other very interesting thing is, of course, microservers. And so these are basically low-powered servers, okay, and where you can actually take. So they usually come kind of in a special kind of cabinet with an interconnect and a whole bunch of very tiny kind of blade servers, and with storage inside it. The interconnect connects the storage up, and usually these systems also have the ability to shut off individual servers. Okay, and so they, of course, in addition to being lower powered, you can actually power portions of your servers down. Okay, so that's so usually it saves on power. That's the motivation. It saves on your footprint because it is extremely dense. Okay, and the feature they have is that the storage is actually, you can take partitions or entire disks and allocate them to different actual servers. Okay, so I think there's a C Micro was a company that I recently listened to a talk to. I think they've been acquired by AMD. So they had a product like this. Okay. Now, so here are the issues to think about. If you were to allocate partitions, it really will not work extremely well. So imagine you've got a partition on a disk, and some partitions allocate to a data node 1 running on a microserver 1, and some to microserver 2, which is another data node, etc. So what will happen is you'll kind of have these systems which are trying to optimize also on spindle usage, fight with each other on spindle, because they have a shared spindle, but they don't really have a shared. They think they have a private spindle, but they actually have a shared spindle. And so that partition, taking a disk and allocating partitions will not work. But instead, if you were to allocate entire spindles, you will not have that problem. Okay? But there's a new problem that you need to. Okay, so if I power down a spindle, power down a server because I find that I don't have need for that compute capacity late at night. Okay, you cannot say I'll power down the spindle that is connected to that, because you have certain replicas that exist over there, and you may suddenly make certain data sets partially unavailable. So what you really want to do is to move it to another server. Okay, and a lot of these microservers will let you do that. And there, the challenge that you need to deal with is 2 challenges. One is not a big challenge. You want the OS to take over that spindle as a hot spindle. So you need to make sure that the OS can take it over, and a lot of OS can do that. The second issue, however, you need to worry about, and it's an Hdfs issue, is that you cannot have, right now Hdfs does not let you have multiple replicas on the same node. And also you don't want multiple replicas on the same node, because you have a node failure, you lost 2 or 3 replicas at the same time. So really, in this sort of thing, which spindle you move where? in a sense, needs to be carefully considered by HDFS as a whole, and it needs to say, okay, these spindles can move in these locations, and then when it allocates its replicas, it doesn't allocate them on two adjacent microservers where they might move the disk back and forth to each other. So you need to kind of have HDFS become a lot smarter and kind of say these groups. So for example, we already do that for VMs. So when we, for example, allocate replicas on VMs, we think of the VM host as what we call a node group. So we'll need the similar concept of a node group to be reused here. So that piece of work is already there, and we'll have to reuse that piece of work again over here. Okay? And so that's the place where microservers could be used. And so this is a change that actually, because of the change in that we made in heterogeneous storage, this is now feasible to do. And what we really need to figure out is microservers something that really makes sense for Hadoop? So people need to do more benchmarks and the pricing, etc. So the underlying, architectural features are there to make this happen. Okay, the change is not there currently in HDFS to allow you to do this. So it's kind of a chicken and egg problem. Is there a demand for this? And is there actually the features in HDFS to make this happen? And this, you'll see kind of this thing, it kind of figured its way out upon whether this happens and how soon this happens. Okay. So I'm going to kind of move to public clouds. Okay. So, about 3 examples of very different user public cloud. The first one, of course, the most common one is Amazon Web Services and Azure, which offer, virtual machines. And so you can go and run anything. And a number of customers actually run Hadoop on these virtual machines. Okay, in Amazon or now in Microsoft's Azure. They also offer Hadoop as a service, so you don't need to install your Hadoop cluster. You want to do a Hive query or something like that, it just works. There are companies like Qubole, which also specializes in offering a very optimized Hive service there. Okay, we have an example of another customer. I am not free to actually talk about the name, but they actually have data that is useful to the customer, so they're offering the customer not only a Hadoop cluster, but also data, and they want to make that data available as one of their value propositions. Okay, and the model here that makes certain things trickier is that the clusters are spun up and down. Okay, which is really great for the compute side because there is no state in compute. You spin it up, you spin it down, there's no problem. So the compute side of Hadoop has absolutely no problems with this. Okay, storage, of course, what happens when you spin it down, you're not going to be spun up on the same boxes, and therefore, what do you do with your data? And all of these systems offer something like an external storage like S3. And so I'll kind of talk a little bit about that because accessing that data offline is a problem. So what people do often is that they either, if they're running a short job, they just accesses of S3. But if they're running a whole bunch of incremental jobs, what they will do is they will move the data and they will do a whole bunch of processing and then shut it down and take the output results and copy it back. So for example, Netflix is an example of a company that does that. There have been talks that they have given at various Hadoop conferences. But now we're going to talk about, can we do a little bit better? I'm going to kind of talk about 3 examples really. So on the next slide. Okay. So let's say I have this Hadoop cluster that I've spun up right now. It has local HDFS. And now I want to, that local HDFS is great for my data that I'm going to create on the fly. Okay, but what do you do about your data that is sitting outside? So normally data that is sitting on S3, you will copy it over. But what actually now Hadoop could let you do is to do a shadow mount. So basically a shadow mount, this is not something that we build, we kind of prototype this, not in the actual Hadoop system right now. Okay, but because of the changes that we made as part of federation, we can basically take a block pool and say that we do a shadow mount of this system. So any namespace operations we forward there, but any of the data operations we direct you to local cached copies. And so we kind of copy the data over and cache it. And so we could keep 1 replica or so worth of data or even do it on the fly. And so basically what this means, you don't really have to copy the data. You kind of, as you access the data, the first few accesses are slow and then it starts just staying in your thing. Okay, and you could decide whether you want 1 or 2 copies. And you get away with 1 copy because, on a miss you can go and get it. So part of this was actually prototyped at Facebook on an earlier system. They didn't quite use the federation block pool because it wasn't there, and it actually worked out pretty well for them. So this is one example where we think of the entire file system as being a shadow mount that caches the blocks, okay? And the other one is, what do you do about writes? So you are creating some output, and you're writing data, and then you'd have to copy the data back out. So the other thing that we are really looking at is to say that, and again, this works very well because of the changes we made with heterogeneous storage, that we now think of the S3 as being a kind of a remote data node and having a fourth replica that sits over there. Okay? But what you don't want to do is as you do a write, you don't want to write to that fourth replica as part of your pipeline or even as a third replica because it'll be slow. Because your pipeline always goes at the speed of the slowest node in the pipeline. And so really you want to think of that as a lazy write. Again, that's why I'm calling it the fourth replica. And then when you shut down the system, you might have to pause a little bit because some of the lazy writes have not been completed, and then you checkpoint your image and you write it out. Okay, so this will basically mean that you come up to your writes also move into that system, and when you want to shut down, you shut down a lot faster because you've been lazily writing the data off. Okay, so these are the two kind of changes. Another very interesting one that we did try at Yahoo. And that we right now have a customer that uses. And so what they are doing is they're offering Hadoop as a service. And they have data that they're offering. And so what they decided to do was to have a top part of the cluster that I have over there in blue. This one there. And these are the data nodes there that basically stores the data that persists across when the compute node clusters are spun down. So the green ones are the compute nodes. They are spun up and spun down. But the blue ones are the persistent data that doesn't get spun up and spun down. And so you keep your persistent data over there. You directly write your persistent data. It is slightly slower, but you get the advantage that you don't get in S3, which is you have rack local speeds. So basically, you get rack local performance, but you don't have local performance. You don't have the advantage local one. You are still going to have Hdfs over here also. So all your intermediate data you're going to store here. You're not going to waste it storing there. And this is actually a system we prototyped at Yahoo. We were going to use it for a completely different motivation reason. That was to deal with scalability limitations, okay? Or to reduce the size of data that is replicated across certain clusters, okay? There was a different use case. Here it is for this particular customer. It's more because they are offering Hadoop as a service, and they are spinning these green clusters. I mean, clusters in this green space up and down, okay? So these are two things that HDF has actually got now the underpinnings to. I mean, this one you can do right now. The previous two that I talked to you about actually can be done because of the changes we made due to heterogeneous storage. And we are working on prioritizing which of these work depending upon what our customers need. Okay, so everything we do, of course, is prioritized by what the market demands. Okay. So now a little bit about VMs. So I only have about 5 minutes left. So here is the traditional motivation for VM is, of course, that you can elastically grow your computation, you can manage your images, you can shrink up and shrink down, okay? And a lot of traditional VM usage depends upon a shared storage system, which is either a SAN or a NAS. And typically a SAN or a NAS does not make sense for Hadoop because Hadoop will just kill your NAS, and it'll also kind of half kill your SAN, and also the SANs are incredibly expensive. So basically what happens is for CPU, it extremely works well, the elasticity. Storage, it doesn't work. So the other one, and I'll kind of come back to that a little bit. The other one is multi-tenancy. So people say, you know what, each of my tenants in my organization, division A, division B, division C, I want to give them their own Hadoop cluster because I get the isolation, I get the guarantees. It turns out really you're better off having a shared Hadoop cluster because the capacity scheduler in Hadoop is extremely good. And now with Yarn, you also have ability to do much finer grained resource management. Originally, Yarn started with just memory, which was roughly equivalent to the slots in Hadoop 1. But now it can actually deal with CPUs, and the architecture below has general enough stuff to deal with I/O and storage and network bandwidth. Okay, so you will see that HDFS will have a scheduler that starts having some of the same features that you see in vSphere, not just for scheduling tasks, but also for the resources. Okay, so the underpinnings are there. If that is your motivation to go and do a private per tenant cloud, really, you're better off having a shared, because the real value in Hadoop comes from shared clusters, okay? Public clouds, of course, all have to use a VM. All of them do, except for one public cloud that I know of, okay? And for private clouds, let me kind of come to that. Okay, so let's come to the elasticity. As I mentioned, compute works well. Data node elasticity doesn't work. You just cannot go and shut down data nodes up and down, because you have to copy all the data out. It's a disaster. So really, data node elasticity does not work. Compute node does work, but there are a couple of things you need to watch out. First of all, you do need to allocate a partition for the local shuffle, okay? And that's something that's going to go away when we start using Hdfs as the blocks as temp storage for MapReduce, okay? But before that, you have, which means you have the fragmentation that is unfortunate, okay, that you don't have in a real non-VM Hadoop system. The second one is that the fact that your VM will also have to allocate local storage means again, you're kind of fragmenting. Even if you have shut down a VM, that vdisk that you store for that VM is sitting there unused when you shut your VM down. So anytime your portions allocated statically, you're fragmenting your storage, okay? And the third one is that local read optimization doesn't work. So Hadoop has now local read optimization for this thing, and that doesn't work in the VM. At some point, somebody may be able to do that, but right now, currently, it's not supported. So that's the few disadvantages even on the compute side. But, compute reasonably works, okay, modulo these things, okay. The other one is, as I mentioned, that I guess I already mentioned this, that the resource management is not necessarily better in a VM. You actually get a much more richer thing. The one thing I didn't mention is another reason for using VMs is image management is so much simpler. Now, that's also changing now. With Docker, you actually have some of the same flexibility, and very soon, Yarn is going to start supporting Docker images, okay? And so you will get the same image management advantages of Hadoop. So basically, if you are using VMs for your private cloud, for test, dev, POC, staging, dynamic clusters are great, okay? You may even share that with known Hadoop, but really for production, you better understand why you're doing it and why are you creating this virtual VM-based clouds. And is a real cloud which shared and using the capacity scheduler and the other parts of Yarn, ask yourself, why isn't that good enough, okay? There might be certain things like, for example, image management that might not be there, but it's coming, okay? So really for production, I would say generally stick with physical machines. If you want to use virtual machines, there are certain caveats on, as I mentioned, about the VM optimizations that we don't have, that we have for the local, and understand why you're doing it. There may be some really good reasons to do it. I'm not saying there aren't any good reasons to do it, but understand the trade-offs, okay? So the other one is an HDFS. Where do we see it moving towards? Right now, what we have is the namespace, really it stores the entire namespace in memory. And we also have federation, which lets you have multiple volumes. So the two big changes that are happening, one that we prototyped last summer with a student who worked for us as an internship, and she basically did storing only a partial namespace in memory, and you said, duh, all file systems do that. How come you guys were the last to do it? So that's something that's coming. The reasons why Hadoop didn't do that on the beginning and why Google File System didn't do that in the beginning. But anyway, what that'll mean is that you'll be able to store, in the order of 10 billion files. You'll be able to have very, very large volumes. And the other one is we're going to start having multiple volumes. So for example, Facebook is already now, has taken federation, is adding multiple volumes. And one of the disadvantages of multiple volumes, people say, is you cannot do a rename from one place to another, and you need to manage your volumes. And that really, in my view, is not a disadvantage, because turns out data does come in chunks that are in separate volumes. So they viewed this as being not a disadvantage at all. Yes, it is theoretically nice to have a research file system that lets you do renames across in a distributed fashion, but in practice, they see no real advantages to that additional complexity of code. So they are actually right now doing volumes, and in fact, once we finish this partial namespace in memory, you'll be able to have a large number of volumes, and you move them around to balance the load. So basically, the number of servers, in fact, you won't call them a name node, you'll call them name servers, will be equivalent to the amount of working set that you want in memory and the amount of load that you want on your name node, and if that doesn't fit, you do it. Yes, you'll have to statically move certain volumes around, but it's not a big deal, in my opinion. And here's a company that's actually doing that, and they don't think it's a big deal either. The other one is you can get n plus k failover. So you no longer need to have 1.1 pairings. You can do n plus k failover. Also, if you want to do the Paxos ring, it becomes a lot simpler with this model because you can have individual Paxos ring. Constantine has a presentation on that. I don't know if it's already done or you're presenting in the next hour. So that's there. And so they will all share. And so this is where we see Hdfs going in a couple of years. And some of the prototypes on this have been done. The next one that we are also right now just starting to work on is really a first-class key value store that we're going to build into the data nodes, okay, using the Hdfs block storage as its storage. So completely independent of the namespace layer. And we will also, as part of this work, support something called mega blocks, which means Hdfs blocks will be stored in these mega blocks so that you can deal with files with very, very small number of small size blocks. Okay, right now, we're supporting the order of 400 million files. If you're not using the HAR file system, we have customers that use HAR, which then gets you a very, very large number. But this is something that's coming very, very rapidly, partly to deal with our needs in a traditional Hadoop cluster, partly to deal with the key value demands of the cloud usage. Okay, so I'm just going to conclude. So storage, of course, is fundamental to big data. Hdfs is kind of the central place to store all your data around which to build, and therefore the term data lake has come apart. And you can build your analytics around it. And Hdfs is kind of a proven rock-solid file system. Some people try to create FUD around it. It has got this deficiency and this deficiency, and they kind of don't do an apples-to-apples comparison. But it's got proven reliability, proven scalability. When we talk about 120 bytes, 20 or 200 petabytes in a single cluster, we don't mean the number of bits to store that. It's actually in production use. Okay, it's been used in a wide variety of applications. It has evolved and continues to evolve, and with a lot of the changes I talked about of tiering and heterogeneous, it basically will kind of move Hdfs to more of a data fabric than just a storage system. So I'll stop there for questions. No, correct. So, yes, in fact, one of the Hadoop as a service, in fact, Ray Misrata, who was instrumental in the starting of the Hadoop project at Yahoo, he's the only company that I know is using Hadoop as a service without VMs. And there he uses name nodes for individual Coke and Pepsi. I don't know if Coke and Pepsi are their customers. And he's also interested in the multiple volumes in a name node. Okay, so the security model in Hadoop is very strong to let you isolate, but you're absolutely right. In fact, more than Coke and Pepsi, Bank of America and Wells Fargo are not going to share a cluster, okay, because the data is even more sensitive. It's financial data. So you're absolutely right in that, and you may want to use virtual machines for that. So like I said, you need to carefully ask why you're doing it, but if it's virtual machines in a public cloud, you have to do it. But if you are doing in a private cloud inside your organization, then the isolation that people talk about, you're better off using Yarn and capacity scheduler. So that was my main point of what is your motivation for using VMs, okay? But thanks for clarifying that. Any other questions? Hadoop? So he's asking about what about the extensions that have been made in Hadoop for virtual systems. So one of the things we have done, as I mentioned, I'm not sure I'm completely answering your question, is that we have put in a change in the topology. There's a topology plugin in Hadoop so that when it allocates blocks, it doesn't allocate them on the same, it thinks it's allocating on two different nodes, but they happen to be on the same VM. So that has actually been there for almost 2 years now. Okay, and that's one thing. And the second one is that there is a plugin called the the location. There's a plugin for location in the name node. I forget what it's called. The replication plugin. Constantly, you remember the name? It slips my mind. So there is a plugin that's been there for a while that also is used by people in the virtual who use Hadoop in virtualized environments. Okay, so there, I'll probably have to go look at that one. It slipped my mind a little bit. We can talk about it enough. You can remind me. You want the question?
Yeah. Just a quick comment following up. These extensions, what they also do, what I think is really interesting is that you can sort of say, I put pure compute VMs directly adjacent to pure storage VMs, right? And then, of course, virtualizing the block layer and storage, that's a tricky part where you have an impact on performance, but then you can also path to physical devices. So that gives you a way to modularize compute and storage. I don't see it as an instrumental concept yet in the distribution. Is there anything that you do?
No, so the main issue that so for example, the recommended way that we have is that if you are doing in your private cloud virtual machines and you wanted to use it, that you would put your base data node and your base VM, your base compute VM in the same physical VM, and then add compute clusters, compute nodes on as needed, okay? That doesn't give you tenant isolation, and if you're happy with Hadoop's isolation, that's good. The second one is you put your shared data on a data node cluster. Either it's on the base system if you are using Linux without a VM, and if you're using VMware, you put it on a VM. And then you have private clusters for each of your tenants, which means this would work if you are in an organization, within an organization, where you want to share data across all your clusters. So still the data pool, this is within a single corporation, okay? So single corporation, you would have your data node as one cluster, and then you have virtual clusters for each of your tenants, okay? It has certain optimizations that do not exist there. Now, what I'm saying that is you better understand why you're creating separate compute clusters. And you better have a good reason because you are actually losing certain performance, okay? I'm not saying there aren't good reasons for it. There may be actually, you better understand, you better optimize for some of these things, okay? We can have a longer discussion on that because we're kind of running out of time here. Any other questions? For the data node that I just mentioned?
Yeah, let's say you want to separate the tenant and you're trying to bring up some VMs and those are all going to be your extra compute capacity. Will those just all point to the same HDFS cluster?
Yeah, so you can actually have, in fact, at Yahoo, before we did the capacity scheduler, Yahoo actually used to run, for many of our internal tenants, we used to run the storage in an HDFS cluster, but then often certain tenants would have their own compute clusters. Sometimes they would also have their own data, but often they would share the main data. So that was we used to call Hadoop on demand, okay? And so that was the mode, and you would do something similar here, okay? But if you're in a public cloud, offering Hadoop as a service, storage, of course, is separate because all your tenants have independent storage. So that model does not work there. I think I should have drawn a picture for that to clarify. I think that would have helped in my next version of the talk. I'll kind of draw a picture to explain that a little bit better because I can see that's kind of hard to visualize. It's kind of natural for me, but I'll draw a picture in the next version of the slide. Any other questions? Actually, in fact, I'm 3 minutes over. In terms of virtualization or in general?
In terms of HBase-specific data access patterns.
So right now, HBase runs. The main things that we have done in HBase is we've done things like co-allocation of your region file so that when you fail over, the failover works a lot more efficiently in this upcoming versions of HBase because it actually uses that some of the features in Hdfs that we've added. The other thing that I see a big thing happening is that with flash storage, we can see Hdfs saying, keep one of my replicas on SSDs. It will not help on writing, but usually Hdfs is very good because it writes sequentially, all the LSM logs. But on reading makes a hell of a difference because it's only reading from one replica, the local replica. So we see SSD with one replica on your local SSD and the rest on other to actually be a big advantage for HBase. Okay, so that's something that you should see coming. So sorry, I'm out of time for questions. So I kind of went a little bit over, but thank you very much.